And that's exactly what brings us next to this storage system hierarchy. Now, if we look at this beautiful triangular diagram, what we see here on the horizontal axis is capacity. So definitely like a larger horizontal axis means larger capacity. What we see here on this right side axis is latency. So lower the better, right? Because we want to take as less possible time to do something. And what we see here on the left side axis is cost per size. So basically the metric to measure cost for these different devices and compare cost. Who wants to cost higher the better or lower the better? Definitely lower the better. Who wants to pay higher, right? If you can get the same thing with the less cost, are we fooled to pay higher for that? No. So cost lower the better. So now in this triangle, what we see is for technologies such as tape, which we rarely see today, we could have very large capacity, but the access latency is also very large, around 100 milliseconds. For one of the most prone technology that we see today in persistent storage systems is hard disk. The access latencies of hard disk is around 10 milliseconds. Now, in terms of cost, definitely hard disks were costlier than tapes when they were invented. But somehow they became more and more affordable, right? So dollar per GB that we could store inside the hard disk became more and more pocket friendly. So we replaced most of the tapes with hard disk. Now, hard disk had its ruling era in terms of persistent storage system for multiple decades. But then in last decade, we saw SSDs overtaking the hard disk. SSDs are still costlier than hard disk. They are not the same, although we have seen a big reduction in the cost of SSDs in last decade. But SSDs provide this nice advantage of much lower access latencies, such as 10 to 100 microseconds. Now from improvement to microseconds, from milliseconds, a very great improvement, right? And that's one of the reasons that SSDs are replacing hard disk, and we are seeing more and more all-flash data centers, things like that. Now, if we further go up into this triangle, next technology is DRAM. DRAM is, again, very long-lived technology, but now we entered into the domain of volatility. So anything below this line is a persistent storage because it is non-volatile. But anything above that line is volatile. So if there is a power recycle, then all the data there would be vanished. We wouldn't be able to get to that data again when we reboot our system. But what is an advantage of such a volatile memory? Well, it provides us with very small access latency. So the access latencies of DRAM is somewhere between 80 to 100 nanoseconds. Now, a jump from microsecond to nanosecond, a very big jump. And as we further go up, CPU caches such as L1, L2, L3 caches, they have even smaller access latencies, but they are even more costly. And they are smaller in capacity because they are costly, they occupy more space, so their space footprint is way higher, and somehow it makes sense to have them in smaller quantities to make this storage system hierarchy much more feasible. And on top of that, we have CPU registers, which are super, super fast to access at the level of around 0.1 nanosecond. but we have very less amount of CPU registers because it's definitely much more costly, and it has very less capacity. So now in this triangle, where do you think persistent memory would fit? Very simple, right? Persistent memory is guaranteeing us the persistence. So it should be somewhere below this horizontal line. But if we put it on the scale of how much time or what are the access latencies to persistent memory, from the table that we saw earlier, we know that the persistent latencies are faster than NAND SSDs. So somewhere here is the best place for persistent memory to sit. And that's exactly where persistent memory fits into our system hierarchy triangle. So now persistent memory still has the property of non-volatile storage, but it can perform IOs directly at the granularity of cache lines accessible from CPUs, same as DRAM. How about access latencies of persistent memory? If we look into the numbers, then we had a big gap from 10 to 100 microsecond to 8200 nanosecond when we didn't have any media between SSDs to bridge the gap between SSDs and DRAM. Now, persistent memories, we see are perfect device to bridge this gap because the access latencies of persistent memory are somewhere around 1 microsecond, mostly lower than that. Why an asterisk? Because, well, persistent memories are still pretty new technology. So we need to know more about it to confirm what's the best we could get out of these technologies. Now, if the world is exactly how we anticipate, then we would have no problems, right? But things gets interesting when we look into real performance. So let's do that. So let's take a look at real performance. First, let's see, because we know that the main advantage of persistent memory is it would allow us much faster bursty IOs. Let's first look at how does it perform with bursty 4 kilobytes random read and write. Now, in this experiments, the results that we see over here, as we are plotting throughput on the x-axis, so higher the better. And when we compare different technologies, as you see over here, we have some of the popular SSDs from popular SSD vendors, Intel, Toshiba, Samsung, etc. And we have two of our opt-in candidates, so persistent memory candidates, where we have Intel opt-in SSD. So Intel opt-in SSD still uses 3D cross-point technology, but it's accessible as how any other NVMe SSD would be accessible through PCIe bus. So it does not sit on the memory bus. While Intel opt-in memory, as now you could anticipate, it's more like a memory because it sits on the memory bus. You would also notice that the capacity of these devices in this experiment is different, and that's just because it's very tough to find all the devices of the same capacity. And thanks to the people who did this experiment and made it available to us to understand about the performance of how these different media of storage behaves and compare them across each other. So here we see that Intel opt-in memory, Intel opt-in DIMM, from like Intel opt-in devices in DIMM form factor, they are clear winner. Like blue bar is way higher than anything else, right? Very perfect. Intel Optane SSD is a close chaser of that, but then other SSD technologies are way away. So this is a very perfect graph that validates everything that we have been talking about until now of Optane persistent memory being better than SSDs. It validates our expectation. But world does not look that perfect as we proceed with comparing some another experiments conducted under some another workload. Let's say this workload at the bottom, which is a random write workload. What we see here is what we would have expected to see on the top is somewhere down here, which is Intel Optane memory performs way lower than many other SSDs and much, much lower compared to Intel Optane SSD. It happens, and this is in real life, this is what we are seeing. Maybe if these experiments are reproduced, reconducted, we might get a bit different results, but this is just for your idea that things in reality, it's important to get your hands dirty, experiment yourself, because always expectations may not be equal to realities. Then further, if we keep looking at still the random IOs, but now rather than bursty random IOs, sustained random IOs, difference between bursty and sustained random IOs is something like if we are looking at a graph where x-axis is time, y-axis is IO arrival time, IO arrivals. Then we see for a bursty IO, we would have less number of IO arrivals, but suddenly at some time, we would have like a burst of many IO arrivals. And then again, less, then maybe another burst, something like that. So this is exactly what signifies such phases of sudden burst signifies bursty IO. While a sustained IO is somewhere is a workload where if we again plot the same similar graph, we would have on an average number of arrivals per time would remain constant. So as you see over here, number of arrivals per time, if we could see like a similar trend across all of them. So for sustained IO, sustained random reads, again, we see that Optane technologies perform good, but here we are seeing Intel Optane memory, which is the dim form factor, that performs a bit lesser than the SSD itself. But when we go to random writes, here the world is upside down. So we see that the Intel Optane memory performs way lower than the Optane SSD and many other drives. So from both these experiments, we see that, well, for random writes, memory, persistent memory and dim form factor might have still a long journey to do good, to improve itself, right? Might still have a lot of scope to show better performance. Now, also remember that whenever we are looking at some data, that data is usually the result of hardware plus software stack. So there are always scope of improvement in how do we utilize any given hardware technology. If we figure out a better way to use any hardware technology, then again, it could change our results, right? It could improve the latency, access latencies that or throughput that we are observing for that device. Next, if we look at the real performance while performing a workload of sequential IOs, sequential reads, and sequential write, pretty much aligned to our random write observations, we do not see Intel Optane memory performing the best, but still somewhere in that top devices domain, right? It's trying to compete. It's good. It's way better than hard disk, but compared to some of the top-notch SSDs of today, we are not able to get that high throughput from this. But also do note this, that the smallest capacity drive that we have in this list is Intel Optane memory, while other memories are way larger, right? A larger memory always has an advantage of extracting more internal parallelism, more level of internal parallelism, and hence producing more better throughput. So just an observation that might take your sight. Finally, when we look at sustained sequential IOs for 128 kilobyte reads and writes, we again see something similar. Now, across all these observations, we saw that Intel Optane SSDs, it definitely performed good in many cases, many different types of workloads. Now, workloads could change. These are just the representation of few extreme cases of workloads where either the whole world is a sequential IO where the whole world is just random, fully random. But most of our workloads that we use practically are a mix of somewhere between neither 100% sequential nor 100% random. So as we see that Intel Optane SSD is doing good, we could anticipate that maybe there is a scope for 3D cross-point technology to be used as a persistent memory. But somehow we have not figured out how to take the best advantage of this device as on the memory bus. Or maybe if we have Intel Optane memory in these experiments that is of larger capacity, then might be we might be able to get like even better throughput for these. But with these anticipations, still it shows a ray of hope to us. So now let's take a look at some of the minuses, or we could call them as opportunities, because with every minus, definitely there is a scope for doing something more, and the scope for doing something more is an opportunity for the better future, right? So let's take a look at this list of opportunities that we still have open to improve this persistent memory technology. First, data is local to process using it. So all the data that resides on persistent memory, it needs to be local to any particular compute process that's using this data. If the node fails and power is lost, access to the data in persistent memory is also lost. Now think a moment why this would be a disadvantage. Compare the similar scenario while using an external storage server. I think you have it there, right? You know the reason. So because now persistent memory is sitting inside the node, right next to the CPU on the memory bus, then if the compute node fails, then definitely the access to the data now pay attention to this. Access to the data in persistent memory is lost. Data may or may not be lost. Again, depends on how we are using persistent memory. We'll soon see there are different modes to use persistent memory, and data could still reside as it is, or could be just vanished. There are in different ways we would end up in different scenarios. The basic access unit inside the TCP MEM, which is Intel Optane Persistent Memory DIMM, is 356 bytes. This is a bit contradictory to when we said persistent memory is byte addressable. But this is the granularity of internal physical access. Why now, leaving the part that it's a bit contradictory, accepting it as a fact, it comes from the physical property of the device. Why is it a minus? Because now any write request that is less than this granularity of 256 bytes becomes a read modified write operation. And is additional read modified write operations good? Nothing in additional is good, right? We want to do IOs only as many as an application requires. We don't want to do anything in addition. If you have to do anything in addition, things like any amplification, write amplification, read amplification, that are not good for any storage device. Appropriate interleaving to manage trade-off of performance and reliability that's required, and it is left upon the user or the software that's that's putting this persistent memory to use. That's left upon them to figure out. The IMC communicates with, which is the integrated memory controller, communicates with Optane DIMM using the DRT interface in cache line granularity, which is 64 bytes, which shares the mechanical and electrical interface with DDR4, but uses a different protocol that allows asynchronous command and data typing. So why is this a disadvantage? Because of shares electrical and mechanical interface. So if these interface, if they're already a bottleneck, now putting a memory which is much larger in capacity that shares the same interface on the motherboard with the traditional memory that we had, such as DRAM, will do no good, right? Because a bottleneck can only lead to a more worst performance if we dependent by multiple components on that bottlenecked resources. Similar to SSDs, Optane DIMM performs an additional internal address translation. What was the address translation that we had inside SSDs? Flash translation. We had FTL, flash translation layer, which translates logical blocks into physical pages or physical blocks. So very similar to that, how SSDs needs to do this internal translation of logical to physical, even Optane DIMMs needs to perform this logical to physical translation. And because they need to perform this additional internal address translation, we would have additional overhead to manage this translation table, right? Every time we have any logical IO, we would have to update this translation if it's a write, or access this translation in order to be able to read that data correctly. Why do we have such translation? Because even in Optane DIMM, similar to SSD again, we have to manage wear leveling and bad block management. In order to do that, we need to maintain some address indirection table. We call it as AIT inside persistent memory. And if we have a translation, we have many other now added tasks to our list of jobs that we need to do within the device.